Hello, my fabulous chemistry students. Video 8, entropy, last video of the unit. Hallelujah. So let's get right into entropy, delta S. What is it and why is it important to us? We're going to get into the motivation for all chemical and physical reactions. And law of thermodynamics indicates that atoms want to be stable. We learned that in the atoms unit. And at their lowest energy state, we talked to that also in the bonding unit, right? And it applies here. These laws also indicate that the universe favors randomness, the disorientated state. Randomness, things just everywhere. I have to put energy in to order them, and then that energy is stored in their order. Okay, they're put togetherness. So the universe likes randomness and disorder because it's lower energy. Okay, this is a little picture in your notes, and we're going to fill in dot diagrams based on phase, and then we'll be able to see the level of order or chaos. Entropy does measure chaos, though, not order. It measures the disorder. So a solid is very structured. The pieces are all tightly packed and not moving. So very ordered. Okay. A liquid, and hence no randomness. A liquid, I think of it this way. If you are a molecule in that solid, you know exactly who your neighbor is at all times because your neighbor never changes. No randomness. In a liquid, everybody is packed together, but there is slightly more randomness because liquids are allowed, the molecules in a liquid are allowed to move around. So your neighbor could potentially change, even though you know the identity of your neighbor, because in a pure liquid, let's say water, every one of your neighbors is water, a water molecule. You just might have a different water molecule in a second as the water molecules move around. Aqueous, again, implies a solution. So there is more randomness now. And notice I color coded that, where there is something dissolved in the water. So now your neighbor molecule could be an Na. If you dissolve salt, could be an Na plus ion, could be a Cl minus ion, or it could be another water molecule. So you just gotta, there's some randomness to what your neighbor molecule could be. And then the most random phase is gases, because now you are all over the place and you are moving in crazy amounts of space, and now everything is completely randomized. So gases have the most randomness possible. Okay, and entropy for us is going to stick mostly to phase. So entropy increases when a sample is turned from solid to liquid, or a sample is dissolved in water, becoming aqueous. Whenever I move from left to right on that diagram, my entropy is going up. Samples are turned from liquid to gases, that would do it, or solids to liquids. Reaction produces a gas as a product when two solids react, because gases are more random than solids. A reaction produces more moles of product than moles of reactant. This piece is for gases only. So when we look at two gases, because that I'm not changing phase, more moles is more random than less moles. Okay, so I have some examples we're going to walk through quick, and you're going to figure out what's what. We're just going to use phase on these examples. So first one I have going from a solid to a solid and a gas. Gas is way more random, so my delta S is increasing. Water, same thing, but I'm going from a liquid to a solid. We know solids phase is less random, so my delta S is decreasing. Here I have two gases forming a gas. Okay, so now I can't change, I'm not changing phases, but I know two things is more random than one thing. So my delta S is decreasing because I'm becoming more ordered. I'm all one thing. That's a lot more order than two things. Solid going to aqueous and aqueous, well, that is moving from left to right on our pictogram, so that is definitely increasing in my randomness. You guys getting a feel for this yet? Solid going to liquid, that's definitely more random. My delta S is going up. Solid going to gas, delta S is going up. So whenever I'm moving left, or I'm going from more moles or more things, my delta S goes up. Whenever I go the opposite way, my delta S goes down. I'm going to save a few of these to do in class as part of the mini lesson. I might as well just finish this side and I'll do the other side in class. Ready? So I have an aqueous and an aqueous going to a liquid. A pure liquid is definitely more random. I'm sorry, less random than aqueous solutions. That's moving from right to left on our phase diagrams. Then I have a solid and a gas going to a gas. I'm going to say two things is more random than one, so my delta S is decreasing. Okay, I will save the other column to do in class for you guys as a mini lesson. And I'm guessing with that we are done with the unit. If you want to go ahead and give those a try, do it. All right.